Okay, the fourth movement, heterogeneity. I was told by a colleague in Quorum who's not here today that Dr. Seuss is sort of played out in these talks. But I figured if I rendered it as a haiku, maybe it's okay. So, one fish, two fish, more. Some are fast and some are slow. They've come a long way. And so this is sort of very explicitly acknowledging the fact that fish are different. Some are fast and some are slow. And that's what a lot of this talk, or the talk, is going to be about. So again, standard sort of random walk model yields this thing called diffusion. So we see that all these things are kind of moving around in the same way, and the eventual distribution spatially is this Gaussian. And this is the standard model for dispersal in a lot of ways. I mean, with a lot of refinements and nuances and stuff. But basically, it's diffusion. And diffusion can be solved. It can be written out as this partial differential equation. It can be solved. And so if you have some advection, with time, you spread out as you move down there. And a issue with diffusion literature is that this kind of constant is sort of defined as this sort of strange limit because it's written out in terms of the partial differential equation, which has these infinitesimal parameterizations. It turns out that as long as you know the length and time scale of movement, it's just sigma x squared over tau. So that's useful. That's another useful application to scale stuff. And your velocity parameter is your advective scale over time, over that time scale. So that's useful. MC parameters tell us again just about everything we need to know about diffusion, like dispersal. But diffusion also has issues about its assumptions. The indistinguishable particles, homogeneous random movements, individualized, and kind of featureless environment is in the simplest case. That's sort of the standard diffusion model. Whereas in fact there's a lot of heterogeneity in the environment. There's population level heterogeneity where individuals have different sizes, sexes, ages, speed, all sorts of stuff. Different behaviors, as we've seen already. Environments change a lot. So heterogeneity is a real issue. And I'm going to talk about some simple ways of modeling population level heterogeneity. Here's a bunch of researchers out in North Carolina. Tagged and tracked, they just individually marked 1,000 of these chub, these freshwater fish, and released them, and saw what happened to the distribution. And what happens is what typically happens in these sorts of studies, sort of a diffusion model doesn't really do a very good job of catching it. There's a few fish that didn't get very far, and a few fish that went very far. And that is called kurtosis, this fat-tailedness. And so they suggest, they model this. They say, okay, they do the Dr. Seuss model. There's fast fish and slow fish. They each have their own individual velocity and sigma. This is what their model looks like. So there's the yellow fish are fast, orange fish are slow, and the yellow fish get further than the orange fish. Pretty simple. And they estimate those parameters. So if there are two groups, then you have 5 parameters. Slow velocity, slow variance, fast velocity, fast variance, and the probability of being one or the other. But if you have k groups, then you need a whole bunch of parameters. So their method, if it's a data well, but it has limitations, if you get a little more realistic. So what do? I say if an individual has some sort of diffusive way of moving, and some parameter is distributed within the population in a certain way, then we just kind of integrate it out, and this is all there is to it, to this heterogeneous framework. It's more flexible than the kind of fast-slow fish in the sense that any distribution will work here, and most distributions don't need that many parameters themselves. And so this is like, here we go, the variance parameter is distributed. Some of these fish are, much slower, some of them are much faster, and it's kind of continuous sort of a realistic sort of population of fish, and we get this sort of distribution. It turns out that if you give a gamma distribution to the diffusion parameter, you get this. This is it. This is the modified Gaussian that integrated out this sort of gamma distributed variance out of the distribution, and it has kurtosis. It has the same mean, the same variance, and has the kurtosis that's constant, that's based on the sort of one of these parameters in the Gaussian distribution. And we can see that there's their fits, and there's my fit. It has one fewer parameter, but it does a good job of capturing that process. So leptokurtosis can be explained by population level heterogeneity, continuous distribution on a parameter reduces the number of parameters, very simple method of parameter estimation, which is kind of bonus feature. So that worked. Now if you go back to these salmon, and here's a dam, just to give you an idea of the obstacles that they go through. The dams have had a lot of negative impact on populations of salmon. There's no question about that. But it provided an incredible opportunity to collect absolutely mind-boggling amounts of data. And a lot of that data is in the form of travel time data. So if we can just sort of illustrate travel time data, here we have sort of Gaussian diffusion fish, randomly moving fish. They're migrating down. We don't know what they're doing in the reservoir, but we can, as soon as they hit this thing, bam, they're detected. And we get this sort of distribution of travel times. And this model, this travel time distribution, has a distribution, it's called the inverse Gaussian distribution, and it's been used to fit travel times. And it does a pretty good job. But it has sometimes, you notice if you look at the data closely, it has some tendency to miss a bit of the peaks, miss a bit of the tails, and so there's something a little bit similar going on to that, that dispersal kurtosis issue. So what if we assume that they're not moving randomly at all, but each fish has its own velocity, and we set them going, so that there's nothing random about the movement, and we saw from the encounter rates that there's reasons to believe that there shouldn't be anything random about the movements, too much random, depending on the situation. And we get this distribution which has a higher peak and sort of a longer tail. One tail that's so long doesn't even make it. So we can do the exact same sort of thing, and we have this other distribution. It's just one over the normal distribution. And you can wonder, so okay, so how do we know which one to use, or which is better? And here's two species. Here's Chinook, yearling Chinook, and we see that they look a little bit more like this sort of diffusion model. And we look at steelhead, and we see that they tend to look a little bit more like this heterogeneous model. So that suggests somehow that they're moving in a different way. That Chinook have more internal randomness, or they're milling more, or they're stopping and going more, or for some reason they're dispersing in a homogeneous way as a population, where steelhead seem a little more likely to, they're better modeled by a model that says pick a speed and go. And you can estimate these parameters, but how do you know which one is right? I mean, how do we know that this curve is because it has an intrinsic variance of 8.3 kilometers squared per day, or because it has a variance in the velocities of 4.3 kilometers per day? Well, you can kind of meld the two distributions. So here's, they're moving randomly, but they have different intrinsic velocities, mean velocities. And we get this thing. And this thing is somehow a mixture of those two distributions. And you can estimate, this is it. This is another monster that I created. But you can estimate all these parameters. The heterogeneity parameter, the variance in the velocities, the intrinsic randomness of the movement. You get this inverse Gaussian reciprocal normal thing, and sometimes it's kind of shows you it can fit something kind of intermediate. For the Chinook, the diffusion model is actually quite good. It's right on top of the red line for this year. Here for the steelhead, it's something that's a little bit higher. And we can kind of estimate, we can get an estimate of the intrinsic variability and the variability that's associated with the heterogeneity within the population. This is more comparisons. If you look at sort of the net heterogeneity sort of as an index, we see that this heterogeneity is really affected by the flows. These are all these different years, all the fish aggregated, migrating in this one reservoir. Very high flow year, very heterogeneous population, whereas the Chinook remain very consistent, very resistant to, the flows don't affect their behavior as much as they affect the behavior of the steelhead in terms of this parameter, which can only be identified with the heterogeneity framework.